My name is Valentin Huber. I'm going to talk about the paper Be Right Back, where we conducted an in-depth study of fault injection effects on FRAM technology. Let's get right into it. So in recent years, more and more previously analog sensors are replaced by digital ones or even smart ones. For example, electricity meter is replaced by a smart meter. And all of those sensors and meters have in common that they need to store and log a lot of data constantly. And for this application, FRAM is a great memory choice. Why is that? First, FRAM is non-volatile, so we don't have to deal with any backup batteries. Second, FRAM is low power. Compared to flash, flash requires high voltages for writing, which is inefficient in terms of power. FRAM uses low voltages, which is more power efficient. Then FRAM offers fast writes, again compared to flash. If you want to update a value on flash, you have to erase the data first and then you can reprogram it. With FRAM, you can directly overwrite it. And lastly, FRAM also offers strong endurance. Again, compared to flash, you only have a limited number of erase and program cycles. With FRAM, you basically have a virtually unlimited number of times that you can rewrite your data, which is quite beneficial for such logging applications. Now, how does FRAM work? FRAM uses so-called ferroelectric capacitors. Those capacitors use a ferroelectric material as their dielectric. Usually this is done with a PCT crystal, which you can see over there. And this crystal can be polarized in two states. So if you apply an external electric field, the zirconium atom, the black one in the middle, moves either into the upper part of the crystal or into the lower part on a base level. And the best part of this crystal is that it keeps its polarization, even though if you remove the external electric field. And this way, we are able to store information in it. Now we need a way to read out the polarization state of the crystal. Here you can see a basic memory cell. And the idea is that you can sense a difference of charge for a switching crystal compared to a non-switching crystal. And usually this is done with such an architecture with a 2T2C model, where you store 1 bit of information in 2 complementary capacitors. So one crystal is polarized in one direction and the second crystal is polarized in the opposed direction. And then you can sense the difference for a switching and non-switching crystal with a sense amplifier. And just like any other memory cell, you have a word line to access the cell, and you have a plate line which you can control the memory actions. All right, let's get a bit more into detail how the actual read works. So the first step is that you have to pre-charge your bit lines on the sense amplifier so that this is in a known state. Usually it's pulled to ground. Then you pull your word line high to access the memory row. And immediately after that, you pull the plate line high to polarize one of those 2 complementary crystals. And then in the next step, the sense amplifier senses the crystal that pushes more charge due to the polarization change onto the bit line. Now, the sense amplifier latches this state, so the terminal where the crystal is connected that changed the polarization is pulled to high, and the other terminal is pulled to low. The actual read is now completed, and you have your value in CMOS available. Now, if we would read again, we have a problem because both crystals are polarized in the same direction, and we would read garbage basically. So we have to restore the original memory state. And to do that, it is really simple. With the write back step, you just pull the plate line low again, but keep the access to the cell open. And then as the sense amplifier latched its state to high where the crystal switched, the crystal gets switched back to its original polarization state. And the other crystal experiences no electrical field, so it stays the way it was. And finally, we can close the cell and perform operations on other memory cells. Writing to FRAM basically works the same. We can skip the polarization and the sense step, and we just force the sense amplifier into the new state of the memory cell that we want to write to, and then we perform the write-back step. But we will only focus on the read operation. So for the read operation, we identified 3 possible vulnerabilities. The first one is if you are able to somehow suppress the pre-charge phase, then your sense amplifier is still in a latched state, and the polarization or the charge from the polarization change will not be sufficient to override that latched state. This means that you will write a value into the memory cell you're just reading that was previously read from another cell. The second vulnerability is that if you induce a fault during the sense step when it's latched, you could, in theory, flip the bit, because sense amplifier is similar structured as an SRAM cell, and then you will write the inverse back to memory in the write-back step. And lastly, there is the plate length timing violation. So if there's a mismatch between the plate length timing and the word length timing in the write-back step, then this will leave the memory cell in an undefined state where both crystals are polarized in the same direction. And this is also the vulnerability where we focused. The reason for this is that it has the advantage that we do not care if the device crashes or not. So for the pre-charge suppression and the sense amplifier bit flip, you need to make sure that the device survives your fault injection. For the plate length timing violation, the memory is already corrupted due to the destructive read from the cell. So we can simply close the cell early. And as already said, we do not care if the device crashes or not. So the solution for that is we can simply use a crowbar glitch, because cutting off the power is the same as closing the cell, basically. All right. Now to test this, we had a look on 4 external memories from 3 different manufacturers. All are of 16 kilobyte density, except one, which was only available in 32 kilobit density, but that should not matter that much. They all share the same SPI interface, share the same commands, and they're all able to operate with 3.3 volt. So we tried to match them as close as possible. And conveniently, they all have the same package, SUIC 8, which we used to mount on our development board, where we also mounted an SMR connector close to the power rail of the chip to ease our crowbar glitches. Now to the actual setup. So the idea is that we read a single byte from memory and then inject a fault and see, then we read again and see if anything changed. For the timing and for the crowbar glitch injection, we used a chip whisperer. And as a trigger signal, we used the MOSI line, because the read opcode is quite a decent trigger, because it's all zeros except the last 2 bits, which are 1, and this transition can be used as an accurate trigger. Now, the timing when you want to apply your fault depends on the physical memory row size of your device. Because usually, even if you only read a single byte from the memory, internally it opens a complete memory row that is, for example, 8 bytes wide. Yeah. And as already said, the glitch length is irrelevant, so you just have to make sure that your device depowers. All right. Now, if you perform that for every memory row of such a memory, then you can plot a heat map, as you can see here. In the upper part, the initial state of the memory is all 1, and in the lower part, the initial state is all 0. Each column now represents a physical memory row, which is for this memory, the FM25, 64-bit wide. So each column 1 memory row, and basically each row is 1 bit line. As we can see, the bit line dominates the outcome of the glitch, which is visible by those stripes. The memory address itself is less important. And this device in particular seems to implement only a single set of sense amplifiers or bit lines, as these stripes go across the complete memory. Now for the second external memory, the CY15, the results look really similar, so I will skip this one and go straight to the third one we tested, the MR45. Again, here the complete memory row is affected if you glitch a single byte. The physical memory row for this memory is 16-bit wide. For visibility, we stacked here always 4 physical memory rows in one column of the heat map. Otherwise, you would get a really long heat map. Again, it's the same as for the first memory. The bit line dominates the outcome of your fault injection. However, this device seems to implement multiple sets of sense amplifiers or bit lines, which you can see by the different light and dark pattern. Right, and finally for the last chip, the MB85, we were not able to identify any parameters that would corrupt the memory. So to conclude the external memories, even if you target a single byte read, you always affect the complete memory row. So the granularity of your fault attack depends on the physical memory row size of your target. Then the bit line dominates the outcome of your glitch. The output has random elements. However, there are tendencies per device. In this table over here, we summarized all bit flip probabilities across all samples. And we can see that some devices are more likely to flip from 1 to 0 or from a 0 to 1 and so on. Yeah. All right, now attacking external memories is a bit boring because if you have a real-world attacker, he could just simply connect through SPI and reprogram the memory as he likes. So how about real targets? For this, we had a look on the MSP430FR microcontroller family from TI. This microcontroller family uses FRAM as its main memory. The memory type is also 2T2C, just as like the external memories, and they have a row size of 46-bit. The device also features some error correction in form of single error correction, double error detection. And now to the interesting part. The device offers 2 debug interfaces. Either it is accessible either through JTAG or through BSL. BSL is a bootloader from TI, which can be communicated through UART. Both interfaces are configurable through so-called signatures, not signatures in a cryptographical sense, but more like a config register, but TI calls them signatures, so I just stick to that. And those signatures are also located in FRAM. Now, the bootloader is always password protected or disabled, so it's not too interesting for us. However, the JTAG is in unlocked state unless the signature is all 0x55 or 0x88. And you can probably see where this is going. Now to the setup for the microcontroller. We first tried to apply the same voltage glitch as for the external memories. However, this had no effect. A paper on the prototype of the microcontroller stated that they implement an internal backup capacitor. And we assume that this microcontroller also implements some form of backup capacitor to prevent the voltage glitching to be effective. For that reason, we switched to an EMFI setup, which we can see here. It's a bit messy, but it works. We're using a chip shouter and a chip whisperer with a 4mm coil that is wound counterclockwise. For the pulses, we used 500 volts. We started to see effects with 480 volts, but they were kind of unstable, so we just took to 500 volts. Now we perform the vulnerability analysis of the target device. Here we performed a grid scan with the EMFI setup. On the top left, there is pin 0 of the microcontroller. And we just tried to glitch during read operations. And then check the complete memory for any modifications. And as you can see here on the top left, we have a really high success rate, up to 100%. Okay, now that we got the location for the EMFI setup, we want to get a bit more into our time frame for the glitch. So we target a single memory row that is really basic. We have a trigger. Then we have an instruction which just copies content from the memory row to register. And then again, we have our trigger routine. And it turns out that our glitch window is roughly 30 nanoseconds wide, where we can repeatedly apply our fault injection. What is also interesting, it's a bit obvious in hindsight, but at that time it was interesting that we were able to modify instructions. So instructions for this microcontroller are also stored in FRAM. And now if the CPU prefetches the next instructions, you're able to fault the instructions, for example, in the trigger low routine. All right, now that we have the timing, we can go further to the actual unlock. So where our target is the readout of the JTAG signature during the start of the microcontroller. The microcontroller requires up to 1 millisecond to start, and that's a rather large time frame for 30 nanosecond glitch window. So we tried to make it a bit more efficient and recorded a power trace to see if we can get any information on the timing. And as we can see on the graph, we did. So with the different JTAG signatures written, the power trace and also the startup time of the microcontroller changes drastically. Somehow, with the JTAG signature is all 0, the microcontroller boots significantly faster. It is to note that the signature with the pattern BVCC does not lock the JTAG. It is still unlocked state, but it requires more time to process somehow. All right. Now we basically have everything we need from the unlock. So we use the reset line as a trigger input. And with that, we can unlock the device repeatedly in less than a minute. You usually require some tries because the error correction will correct single bit flips. However, this is usually just a couple of seconds with a couple of tries, and then your JTAG is unlocked. It does not matter if the device is either fully locked or password protected. The bits just get scrambled, and you have a completely unlocked device. And I did not test this yet, but this should work for all devices of the MSP430 FR5 and FR6 series, as they all share the same debug locking mechanism, according to the datasheet at least. All right, and now to conclude my talk, we saw that the FRAM read operation is vulnerable to fault effects. We showed that the JTAG of a real-world target can be unlocked with this vulnerability. And we see finally that the vulnerability must be considered during design time, and you must be cautious to not just replace your flash memory with FRAM memory without considering any security implications. All right, that's my talk. Thank you, and now I'm happy to answer any of your questions.